Everyone, today I will talk about R structures, complex conjugation, and cartan subgroups. This is the paper authored by Pete Clark. That is the paper titled Elliptic Curves over Real Number Fields. I will read to you the section 3, point 1, orders and ideals in imaginary quadratic fields. Let K be a number field. So K is an imaginary quadratic field. A lattice in K is a Z module. A lattice in K is a Z module. That is a Z module of rank 2. So there is an action of Z acting on the module. So it is a Z module. Lambda belonging to the K. It is obtained as the Z span over a Q basis for K. So this is the explanation of the Z module. It is a Z span of Q basis for K. An order O in K, order O-R-D-E-R, order. An order in O is a lattice. So an order is also a lattice. And the lattice is a Z module. What is the relationship between the order and the lattice? That is the essence here. So if you can understand the relationship between lambda and O, you can understand this paper, and you can understand complex multiplication of elliptic curves. So an order in K is a lattice, which is also a subring. The ring of integer OK. So this is its explanation here that the most simplified version of O is OK. That is the maximum O. The maximum order inside the K is OK. The ring of integer OK is an order of K. So ring of integer is like for example A plus BI. A plus BI is a ring of integer. So the ring of integer OK is an order of K. Conversely, since every element of an order is integral over Z, so the key point is that it is integral. Since every element of an order O is integral over Z, O belongs to OK with finite index. So O belongs to OK. OK is maximum. And the O belongs to OK with finite index. For any lattice lambda, we define a function O of lambda. That is, O is a function of lambda. So I asked about the question previously that what is the relationship between O and the lambda? So I answer it now. O is a function of lambda. So what is the relationship between O and lambda? The answer, O is a function of lambda. So O of lambda is a set where if X belongs to K, then the condition is that X times lambda belongs to lambda. So X times lambda belongs to lambda means that lambda is an ideal of K. Right? Because X times lambda belongs to lambda. But X times lambda belongs to lambda, but the set is O lambda. O of lambda. And O of lambda is an order of K. So lambda is a fractional or lambda ideal of K. So there are three layers. There are 3 layers of containment here. K is the biggest circle. O lambda is the second circle. Okay. Then O is the third circle. And the kernel is lambda. So first layer K. Second layer O lambda. O of lambda. the set third layer O, and the kernel is lambda. You can think about it in this way. So O of lambda is an order of k, and the lambda is a fractional order of lambda ideal of k. For O alpha belongs to k cross. K cross means the multiplicative group of k. For O alpha belongs to k cross, we have O of alpha lambda is the same as O of lambda. That is the definition of a fractional O of lambda ideal. The property is that O of alpha lambda is equal to O of lambda. So alpha times lambda, you can view alpha times lambda as a way to rotate the basis, because lambda can be viewed as a basis. Because lambda is what is lambda? So a lattice in K is a Z module lambda obtained as a Z span of a Q basis for K. So a lambda is a lattice, and a lambda is a Z span of Q basis for K, right? And we know that an order is a lattice, which is also a subring. So lambda is a kind of Z module, right? Because a lattice in K is a Z module, and because K is an imaginary quadratic field, so lambda is a Z module of rank 2. So there are two bases, right? For example, you can view lambda as 1 and I. Two bases. The basis is 1 and I. And the lambda can be viewed as the Z times I plus Z times 1, right? So lambda as a base has two bases. The first basis is 1. The second basis is I, where I is the square root of -1. So lambda, there are a lot of different lambdas, but one of them can be viewed as Z times 1 plus Z times I. And if we have alpha belongs to K cross, and alpha times lambda, it will rotate the lambda. For example, I1 and I are two bases, and we use alpha to times lambda. It will become, for example, a different rotation. For example, it becomes 1 and tau, where tau is A plus BI, for example. So from two bases, from lambda, where the basis is 1 and I, to a different lambda, from lambda to lambda prime. The basis of lambda prime is 1 and tau, where tau is A plus BI. And this is a kind of a rotation. Okay. So for O alpha belongs to K cross, we have O of alpha lambda belongs to O of lambda. And O of alpha lambda is equal to O of lambda. For any order O, a fractional O ideal lambda is proper if O is equal to O of lambda. So the property lambda is a proper lambda. That is a proper ideal if O is equal to O of lambda. So O of lambda contain O, and if a lambda is proper, then O of lambda equal to O. A fractional OK ideal is necessarily proper. So a fractional OK ideal is necessarily proper, whereas for any non-maximal order O, the index of O times OK, the index of O inside OK times OK is an O ideal, which is not proper. Okay, thank you very much.